I'm Rohit Kumar Singh, the teaching assistant for the course Experimental Physics 2, and this is the 11th live session for this course. And so for today, I'm going to show you some more examples on polarization, which we discussed last week also, and I'll uh, recap a little bit about polarization, some concepts, and then continue to the examples. Okay, so let's start. So I uh, discussed some concepts of polarization. So yeah, so what is polarization basically? Uh, do you have some idea what is polarization? Satyanarayan? You can unmute and answer if you know. Otherwise, it's fine. Hello? Okay, it's no problem. So, polarization is so in general, uh, the light that we see around us is not polarized. That is, uh, it's not uh, confined in a plane. Okay, so the definition of polarized light is light wave confined in a particular plane. Okay, or in a particular direction, or in a particular geometry. So we'll see there are other different types of polarized light. Like we have linearly polarized light, we have uh, uh, which we also call plane polarized light. Then we have circularly polarized light. Then we have elliptically polarized light. So we have different kinds of uh, polarization. Okay, and so basically, if you want to like represent these polarization, we can do that in a simple manner. So suppose you have this. Suppose this is your y-axis, this is your x-axis, okay, and this is the z-axis, okay, and now a linearly polarized light. Uh, so if we have a single wave, which can be represented like uh, suppose y is equal to some magnitude sine kx minus omega t. So this is an equation of a traveling wave, okay, and it can be represented like this. So it's clearly linearly polarized light, because uh, if there is an observer somewhere here, so let me from yeah. So suppose this is the, then he will see just one direction. So if someone views this coming incoming wave from the z-axis, he will see that only he will see that the vector is vibrating in a particular direction, right? So it's a linearly polarized light. Or what you can do is, if you have two plane polarized light, one is in the y-axis direction and another one in x-axis, so something like this. Okay, so let me change the shade. So this one is in x direction. Then you will get a resultant, and the phase difference between them is 0. Okay, so then what you will get is uh, a, a wave, a resultant wave, which is in which will be at 45 degree. So like this, right? My drawing is bad. So, and which when viewed from here, so suppose this is your y and this is your x, it will look like this. The vector of this polarized light, this resultant wave will look like this. So it's a linearly polarized. So it's a linearly polarization. An example. So y and then sorry, you can write the x wave as, so with the same amplitude and no phase difference. Okay, so this should be z. Okay, so similarly we can have circular polarization and elliptical polarization. For that, what we have to do is we have to just introduce some phase difference between the two waves. So uh, if we have something like, so, so now if we have something like y is equal to, uh, let's keep it the same, and in x let's introduce some phase difference. So we'll introduce here a phase difference of pi by 2. Okay, so it's advanced by pi by 2. Okay, so now what it will be look what it will look like is, so let me try to draw it. So suppose this is your y, this is your x, This is a z direction, and then so for the y direction, you have the same wave that we had before, but in the x for the x direction, I mean the wave vibrating with the electric field vibrating in x direction, uh, we are starting from phase difference of pi by 2, right? It's advanced by pi by 2, so it will be like this, this, right? So okay, and uh, the resultant will look, so suppose, so if someone is looking at it uh, from the z direction, he will see that the resultant electric vector, it's moving in a circle, okay, like this. Now, how do you understand it? How it's moving in a circle? So let's see. Here at the origin, you have electric field vector uh, starting from here. I mean like this. Okay, in the y axis. Then slowly, when you take the resultant of these two at pi is equal to at z is equal to pi by 2, uh, then it is at some angle with respect to y-axis, okay, and this angle changes gradually, and so you uh, get your electric field vector uh, at all the direction. I mean at all the angles. Uh, so you get a circle, okay. So let me try to visually represent it. Uh, so suppose this is the y-axis wave, okay. Sorry, this is the x-plane wave confined to zx plane, and then you have the wave confined to uh, yz plane, okay. So at this place where this uh, xz wave is 0, you have electric field vector in the uh, y-axis, in the direction of y-axis, okay. But when you have some magnitude of uh, wave at in the xz plane, then you get your electric field direction like this. Then it starts change. It keeps changing, okay, until this yz wave becomes 0. Then you have your direction uh, the electric field direction is in xz direction, okay. So you see this electric field is rotating from 0 to 2 pi, and so if someone is viewing from z axis here, he will see a circle, right? He will see that the electric field vector is making a circle. Do you understand? Okay, yeah. So in the same way, so this is the case of circular polarization. Right? Now in the same way, you can have elliptical polarization, right? So for elliptical polarization, uh, what you need? So you need any arbitrary angle. So suppose if the phase difference is pi by 4, here the phase difference was pi by 2. Then looking from the z axis, you will see that the electric field vector is making this kind of this ellipse. Electric field vector is moving in ellipse, right? So yeah, this way you can produce different kind of polarization. So these are different types of polarization exists. Okay, and yeah, yeah, you know the so I mentioned some formulas some laws of polarization last time, like Miller's law and polarization by reflection. Do you remember it? I mean, do you know those concepts, or should I go over it again? Do you know Miller's law? Yeah, that one. Yeah. So if you have a polarizer and unpolarized and a polarized light is passing through that, and then you have another polarizer, then the intensity after emission will depend on the angle between the two polarizers, right? So it's I naught cos square theta. So yeah, okay. Then let me go to the problems. Okay, and see how to deal with them. Okay, so first problem for today. Uh, when the angle of incidence is 60 degree on the surface of a glass slab, it is found that the reflected ray is completely polarized. Then it is asking the velocity of light in the glass. Okay, so you have a glass slab, something like this. Okay, and this is the normal, and a light is incident at 60 degree. Okay, and it is found that the reflected ray is completely polarized. So reflection will be at 60 degree and it is completely polarized like this. Okay, polarized in a plane. So then it is asked that what is the velocity of light in the glass? Yeah. Okay. So how do we solve this problem? Any clue? Satyanarayan, do you know? Do you understand the problem? Okay, so do you know the solution or should I help you? Yeah, yeah. So what does so what is Bristol law? Uh, I mean, uh-huh. Yeah, but what is the concept behind it? Like, how do you get that equation? Do you know? You are right. I mean, you are right. Mm-hmm. Yeah. Yeah, yeah. So the concept here is the polarization by reflection. Okay. So what happens is that if an unpolarized light falls on a dielectric medium, okay. So what happens is if the reflected and refracted light are at 90 degree to each other, then the reflected light is polarized, right? Right. So this is referred to as Bristol law. And to satisfy this condition, this incident angle is given as tan inverse of so this if this medium has refractive index n2 and this one is n1, so n2 by n1. Fine. Now here this angle of incidence is given 60 degree. Okay, and so and this medium is air, right? And so it's in fact n1 is 1 essentially here, we'll assume it. So uh, we can calculate the refractive index of the glass slab, right? Which is simply tan 60 degree, correct? And which will be what? Under root 3. Now what is the velocity of light for a medium whose refractive index is n2? So so you know that refractive index is defined as uh, so refractive index is defined as the velocity of light in the medium divided by velocity of light in the vacuum, right? Yeah. So the velocity of light in the medium is simply diffractive index into speed of light. Oh, sorry, sir. Uh, did I wrote it correctly? Is it refractive index is oh C by V. Yeah. C by V, right? C by V. Yeah. So otherwise, it will be always less than one. Okay. So the velocity of light in the medium will be just simply C by N2, which is 3 into 10 to the power 8 divided by under root 3, which is 3 under root 3 into 10 to the power 8. Correct? C option. Is it fine? Okay. Thank you. So I mean this is I mean formula is there. Okay. There is no problem. I mean it's a simple problem. But what you have to understand here is that just by performing this experiment can be performed in a lab, right? You can shine light at 60 degree on a glass slab, right? But just by measuring, I mean this polarized light, uh, just by measuring the reflected light, you can calculate the velocity of light in that medium. So that's the beauty of this simple experiment that you can perform. Correct? So you have to think, you don't have to think about these problems like just solve it and move on. You have to think what this implies about the nature, right? What information can you extract from a simple experiment? Because this course is experimental physics, right? So this thing you have to keep in mind. Okay, so next problem. What should be the phase difference between two plane waves of equal amplitude to produce circularly polarized light? So I just mentioned in the beginning, to produce a circularly polarized light, the phase difference should be what? I showed you. Hello? So if you have two plane waves, so suppose like this, and y is sine, sorry, and some angle phase difference is there. Okay. Now to produce circularly polarized light, what do you want the phi to be? Phi should be what? What should be the phase difference? Is it pi, pi by 4, pi by 2, pi by 3? What should it be? No. Why pi by 4? I calculated it here. Na? See, when I was discussing polarization, I showed you if you take pi by 2 difference, then we will get circular polarization, right? Okay, so it's simple. I mean, you don't have to remember it. What you can do is, so this is uh, x and y. So these are two plane waves, right? One is confined in xz direction, one is in yz direction, right? So what you can do is take the square of these two, okay, x square and y square, and add them, okay. A square sin square kz minus omega t plus a square sin square kz minus omega t minus 5. Fine. Now you know what is the equation of a circle? Yeah. So you want to have, so let me take a square common, okay. So then what remains here is, sorry, hmm, minus plus doesn't matter, minus 5, correct? Okay. So you want to go this to 1, right? Then you will have a circle, equation of a circle, right? Now how to make this uh, quantity 1 equal to 1? So you have this sine square. If somehow we can make this quantity cos square kz minus omega t, then cos square plus sine square theta, you know it's 1, right? And to make this quantity into cos square theta, you need to take phi is equal to pi by 2, correct? Yeah. So if phi is equal to pi by 2, then what will happen is x square y square is equal to a square, which is an equation of a circle, right? So this way you can also understand. In what case? Mm-hmm. Mm-hmm. No, no. So you need also this amplitude to be the same, right? Yeah, this condition should also satisfy. Yeah. And if you have some other angle like phi equal to pi by 4, then the equation that you will get here is of ellipse, or I mean different kind of ellipse, right? But for circle you need phi equal to pi by 2. So This way you can also think. Okay, then next problem. The velocity of light in a medium is 2.4 into 10 to the power 8 meter per second. What is the polarizing angle of incidence? So this is the reverse of the first problem, right? Now we are given velocity of light in the medium and we have to calculate polarizing angle of incidence. So we know what is the what is the refractive index? It is C by V. That is speed of light in vacuum and divided by speed of light in medium, and which is just 3 into 10 to the power 8 by V, and we have n equal to 2.4 into 10 to the power 8, both are in meter per second. So V is equal to just 3 by 2.4, which is 1.25. Correct? Oh, sorry, sir. Uh, N is equal to, okay, yeah, it's correct. Fine, right? Then we have to calculate the polarizing angle, which you know the formula, which is just tan inverse of refractive index, and tan inverse of 1.25 is what? So you can calculate it using calculator. It is 51.34 degree. Fine. It's the same. It's the just opposite problem from the first problem. So with these two problems, problem 1 and problem 3, you can have a nice experiment. So from the first problem, what you can do is you can determine the velocity of light, right? In the first problem, we have determined the uh, velocity of light in the medium. And then what you can do is uh, you can perform the experiment again, and you can calculate the polarizing angle of using some different source of light, you can calculate the polarizing angle, right, of that source of light. So it's a nice application. Hmm. Yeah, yeah, yeah. Okay. Mm-hmm. I don't get your question. So you are saying in the exam the problems are not easy, or what? Mm-hmm. Oh, oh, okay, okay. They are missing. Yeah, yeah. Oh, okay, okay, okay. Hmm, hmm, hmm. So, okay, I'll maybe request the professor to include some important, I mean these constant values. Mhm. Yeah, 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 yeah. Yeah, that's necessary. Okay, I'll talk to them. Okay. Okay, let's go to our next problem then. So here, an electromagnetic beam has intensity 20 watt per meter square. Okay, so intensity is given, which is 20 watt per meter square, and is linearly polarized in a vertical direction. Okay. Now, what is the intensity of the transmitted beam if the angle of incidence on the polaroid is 45 degree with the vertical? So, so this problem is like this. So suppose uh, you had an unpolarized light, it passed through a polarizer which has the polarizing axis in the vertical direction. So now you have this linearly polarized light of intensity I I naught, which is 20 watt. Then uh, then you have a polaroid which is which is aligned at 45 degree like this. Okay, with the vertical. So this angle is 45 degree. Then you are asked what is the intensity here after passing this polaroid. So this is a straightforward application of Miller's law, right? Which is I is equal to I naught cos square theta, correct? Where I naught is given 20 watt per meter square and theta is what, 45 degree. So cos square 45. Cos square 45 is 1 by 2. So it's just 10 watt per meter square. So the intensity gets half, correct? So easy problem. Any question? Okay, thank you. Okay, then next problem. A tube of length 12 centimeter. So you have a tube, okay, it's 20 centimeter, sorry, 12 centimeter, and it contains a 20% sugar solution, okay. So do you know what sugar solution does to a polarized light? If there is a polarized light going inside, what does the sugar solution does? Uh, yeah, the formula I know, But what I mean, how this sugar solution rotates the uh, plane of polarization? What is there in the sugar solution? Do you know what material is there? What kind of chemical is there? You're right. The specific rotation is tan theta by LC, right? Where L is the length of the tube, C is the concentration. So this sugar solution, uh, if you have studied some chemistry, you know that you know about chirality. Do you know chirality? Okay, maybe you can look at it later. So it's an optically active uh, solution, okay, and which rotates the polarization of light which is incident on it, and it depends on uh, how long the light travel in the medium. Okay, so that's why this length factor is there, and these experiments are there in BSc, where you calculate this specific rotation. Uh, it's an easy experiment, can be performed very easily. Okay, so yeah, so let's just calculate the value. So 10 theta is given here, which is 18 degree, and we'll get the value in degree, and the length is given as 12 centimeter. So 20% sugar solution means the concentration is what? 0.2, right? Gram per centimeter cube, correct? So if you perform this calculation, you will get the answer as 75 degree. So this light after emission will be rotated by 75 degree from the original direction. Okay. Yeah. Now sixth problem. Uh, Here, an unpolarized light is incident on a surface of a medium of refractive index 1.62. Okay, so suppose you have a medium, its refractive index is 1.62. So, what should be the angle of incidence such that the reflected and refracted rays are perpendicular to each other? So this is the incident light, and the question is, what should be the angle between refracted and reflected light? So I mean, this is a very easy problem, right? You know the Brewster law, correct? Yeah. So yeah, so if they are if the reflected and reflected light are perpendicular to each other, then we can simply write the incident angle as tan inverse of refractive index, right? So, and which is uh, so tan inverse 1.62 is simply 58.3 degree, and angle of reflection and angle of incidence is same. So yeah, the correct answer is B. It's an easy problem. Okay, so let's go to the next problem. Here, the question is a polarized light of intensity 40 watt per meter cube. So I naught is given, is incident on the analyzer in a certain angle, at a certain angle. Okay, we don't know the angle, but we know that the transmitted beam has an intensity 30 watt per meter square. Okay, so after passing through the analyzer, the intensity reduced to 30 watt per meter square. Then we are asked the angle between the transmission direction of polarizer and analyzer. So again, we can just use the Malus law. Okay, and cos square theta would be just I by I naught, which is 30 by 40, that is 3 by 4. So cos theta will be under root 3 by 4, which is under root 3 by 2, which is just 30 degree. Sorry, 60. Hmm, 3 under root 3 by 2 cos theta is 60 degree, right? Uh, I mean, cos inverse 3 by 2. Wait, cos 60 is what? Half, right? 1 by 2. Hello, hello. Can you hear me? Yeah. Actually, the Wi-Fi went on, but I'm reconnected to another Wi-Fi. Okay. So yeah, where were we? Okay. Uh, okay. Can you see the slides? Okay, thank you. So, yeah, what I was saying, so cos 60 is 1 by 2, right? I mean, cos 30, so the theta should be 30 degree, right? Yeah, but here the options are all wrong, I think. Okay, it should be 30 degree, no problem. Okay, it's clear, right? This problem. This is just an application of Miller's law. Okay, thank you. So next problem. Here we have this problem. A quarter wave plate induces a phase difference of blank between O ray and E ray. Do you know what a quarter wave plate and half wave plates are? Mhm. So why they, why they maintain a phase difference of uh, lambda by 2 between O ray and E ray? Why is that? Mhm. Yeah, yeah, but I'm asking, but I'm asking why it happens. Why E ray and O ray behave differently in such a material? Yeah, yeah. So yeah, the so if you have a calcite crystal, you know about calcite crystal, right? Yeah. So there is a phenomena called double refraction. Yeah. So because of that, uh, one, I mean the ordinary the light ray which enters the calcite crystal, it gets divided into O ray and E ray. Okay, where the depending upon the negative, so calcite is a negative crystal, right? Its refractive index for E ray is less than the refractive index for O ray. Okay, so E ray will travel faster than the O ray, correct? And so, uh, and you have and so you will have a path length difference, which in turns give a phase difference between the two, correct? And so quarter wave plate means quarter of a wavelength, which is lambda by 4. Half wave plate means half of the wavelength, lambda by 2. And if you convert this into a phase difference, this will give you pi by 2, and this will give you pi, right? So here quarter wave plate induces a phase difference of pi by 2, correct? Okay. And then half wave plate induces a path difference of lambda by 2, pi by 4. Lambda by 2 I just mentioned, right? Phi is not there in terms of wavelength lambda by 2, right? Yeah. Okay. Okay, then our last problem for today. So, what will be the angle of refraction in the glass if the polarization of for the air glass interface is 55 degree? So, again, it's a very simple problem. Can you suggest the solution? So, you have a air glass interface and angle of refraction is asked, okay, and the polarization angle uh, is given as 55 degree, correct? So for polarization, these two refracted and reflected light should be at 90 perpendicular to each other, okay, and this is 55 degree, so and this is 90 degree. So refracted this angle, so adding up all these three angles should give 180 degree, right? So 90 plus 55 plus r is equal to 180. So r is equal to 180 minus 90 minus 55, which is 35 degree, correct? Hello, Satyanarayan. Yeah. Yeah, easy problems, right? So yeah, this is the last problem. Uh, so yeah, do you have anything to ask? Anything that you want to discuss or anything you want to say? So can you please tell me about yourself? Like where are you from? What are you doing? Uh-huh. Okay. Oh, you are assistant professor there. Oh, nice. So what do you teach usually? Oh, applied physics. Nice. So, what level of courses do you teach? Mhm. Okay, okay, okay. So, mhm, okay, okay, okay. So, on Saturday also you have class to teach? Oh, okay. Uh, mhm, mhm. So, why did you take this course? This course is should be easy to, for you, right? I mean, it's That's nice. Okay. Do you want to ask anything? Hello. Uh-huh. Mhm. No, no. So, like I said. Mhm. Yeah, yeah, yeah. I understand. Okay. So, like I said. Mhm. 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 Any easy explanation you want, right? Okay, okay. So, see, the ordinary light that you are seeing right now, okay. So, you know that the light is made up of electromagnetic waves, correct? So, let me go to some empty slide. So yeah, okay. So, a light wave, a light wave is an electromagnetic wave, okay? And so what happens is that in a light wave you have both electric and magnetic vectors. Okay, it's an electromagnetic wave. But when we consider this phenomena of optics, we only consider electric uh, part of the electromagnetic wave. Okay, magnetic part doesn't contribute that much. Okay, so now uh, what you can do is uh, if you want to write an equation of a wave, okay, like I wrote, so suppose this is your x-axis, y-axis, and z-axis, okay. Now you want your wave to travel in z direction. You can, you can choose any direction. You can choose y, x, but for now I am just choosing z direction, okay. And your electric field is, so the electric field vibrates, okay. it uh, so the way the electromagnetic field propagates is, so this electric field vibrates in a particular direction, and the equation can be written like this. So suppose x equal to some amplitude sine kz minus omega t. This is a standard equation of a traveling wave, right? So what will happen is that at z equal to 0, you have sine minus sine omega t, correct? And if the time is equal to also 0, then the amplitude of x is just 0. Then at some other time, I mean, it will have some sine component, okay, and it will start going like this, correct? So in an ordinary light, what happens is that uh, there is no fixed uh, plane of vibration. Okay, uh, this x-axis is not fixed. I mean, it changes this direction. Sometime it vibrates like this. Sometime, I mean, everything is a mixture there. Okay, this whole thing is a mixture. So, and when we place a polarizer, a material which polarize the light. So, polarizers is mainly made up of Nicol prism. You know Nicol prism, right? Nicol prism is another material which has the property of double refraction. So, what it does is it eliminates the other. I mean, it only let. So suppose an unpolarized light is coming inside a Nicol prism. What will happen is that uh, all the other components will remove. Only a single component of light which is polarized in one direction will pass through. Okay, it is the property of the material. So you will get a linearly polarized light. Okay, and this way you can get two linearly polarized. So then you can maybe rotate the Nicol prism in 90-degree, and you can get a polarized light in, suppose, y direction. So one in x direction, one in y direction. So suppose, and then what you can do to get a circularly polarized light, you can superimpose those two lights together. Okay, two linearly polarized light, one is like this. Okay, it's vibrating in x direction, and one is this, which is vibrating in y direction. Okay, now you see, so suppose, consider this origin here. The electric field vector is 0 because both are 0, right? Now some, at some other places, one electric field vector like this, another one is like this, right? And since they are at 90-degree to each other, the resultant will be where? At 45-degree, right? And 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 this will happen for all the other places. So with these two linearly polarized light, you will again get a linearly polarized light at at 45-degree, right? And when you change the phase difference between two, so what you do is you start one wave from origin, other one at pi by 2, correct? Now what you will get, while what you will see is that this electric field vector, it starts from, so suppose it is like this, but here it starts rotating. uh, so so suppose this is your y-axis, this is your x-axis, and suppose the z-axis is coming out of this page. Okay, so what you will see is that first, so suppose first the x component is 0, so electric field vector is like this. Okay, then what will it will do is it will go like this, 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 this. Okay, it will perform a full circle as the wave propagates, correct? So This way you can visualize. I mean, you have to think about it. There are many good pictures in books also, but essentially it's the same thing. Okay, just you have to take the resultant of two vectors. One vector is in x direction, one is in y direction. Okay, yeah. So yeah, think about it, and things are not clear. Maybe in the next meeting I can explain it more. Maybe I can show you some video or something. Okay, I'll try to look for it. Okay. Uh, okay. Thank you. Thank you for joining. See you next Saturday. Next will be our last live session. So yeah. Okay. Thank you. Thank you. Thank you.